Is it visible? Okay, seems good. Okay, so yeah, thank you for the introduction, the invitation. So let me just begin by describing the model, which is that of a Lozenge Tilings. So we'll start with this triangular lattice T. Its faces are all triangles. And we'll say that a pair of adjacent edges is a tile. We can also call it a lozenge or a dimer. So I've given three possible examples of orientations of these lozenges shown to the right over here. It can be bound, along the bottom edge, along the right edge, or along the left edge, which form three possible orientations for how these dimers might look. And what we'll do is we'll be considering tilings of subdomains of T using this triangular lattice T using these lozenges. Okay, so I'll give you a few examples. First, I've shown an example of a tiling of a hexagon of side length 2. Okay, so I can also say that these Lozenge tilings can be interpreted as step surfaces or height functions. So to see this, you might observe that Lozenge tilings kind of look like a bunch of cubes stacked on each other. For example, in this picture over here, I have a hexagon, like a 3 by 4 by 5 hexagon. And sort of down here is the base of it. And then I'm packing cubes up here, which are kind of going up to the top. So a cube would look something like this over here, 3 lozenges in all different orientations bound together. And then you see like little copies of this everywhere in this tiling. And that way, if you imagine that these lozenge tilings are just a bunch of cubes stacked on top of each other, you can assign a height function to the tiling in sort of a fairly natural way, just by looking at the number of cubes above a single vertex. Okay, this is somewhat non-rigorous at the moment, so let me give you a more direct definition, which is the following. So this cube here, this set of 3 tiles bound together, it gives you sort of a natural way to evolve the height function. Namely, if the height function is h down at the bottom of this bottom left corner over here, it tells you that h had better be 0 here, 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 and h plus 1, 0 here, 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 and here. Namely, more specifically, so if I have a lozenge that's pointing to the right like this, the bottom 2 vertices have to have the same height, and the top 2 vertices have to have the same height, which is 1 above the bottom 2 vertices. Likewise, for the vertical tile, the left 2 vertices have to have the same height, and the right 2 vertices have to have the same height, which is 1 above the left 2 vertices. So in this way, this kind of gives you a rule to locally, given a tiling, I can locally propagate the height function up by just following the rules in this cube and defining the height function everywhere like that. Okay, so anyways, I guess that's a bit of an aside, which is how you can define a height function from a Lozenge tiling rigorously. But you can also just see it kind of if you see the 3-dimensional picture, it should be fairly obvious. Okay, so we call the boundary height function the restriction of the height function to the boundary of the domain. So for example, for this hexagon, the boundary height function is 0 along these 2 sides. It's 3 along these 2 sides, and it's linearly increasing along these remaining 2 sides. Okay, so the boundary height function depends only on the domain and not on the tiling. This is a fact that you can kind of convince yourself of combinatorially. And any height function with this boundary data corresponds to a tiling. So I can go kind of back and forth between height functions and tiling. So I will often just use the 2 words interchangeably. Okay, so the basic question I'll be interested in this talk is how do random tilings on large domains look? So we'll be considering uniformly random tilings of fairly large domains, so which one might also interpret as the dimer model on subdomains of the hexagonal lattice. We'll pick one at random, and we'll want to know what it looks like. So the most basic example maybe is I take this hexagon over here, a fairly big one. I take one of many possible Lozenge tilings of it at random, and I ask myself how it looks. And you can immediately see that there's quite a bit of structure. First, there's this circle, outside of which everything seems to be kind of fixed. I mean, you have this sort of shingle work pattern happening in the corners outside of the circle. But inside the circle, everything is kind of disordered. So I'll be interested in properties like this, sort of more fine scale properties about these random tilings. Okay, so the first, which I kind of alluded to just now, is that this Lozenge tiling will satisfy a sort of limit shape. Okay, So there are several ways of trying to explain what I mean by this limit shape. I'll do so in terms of the height function. So as I mentioned before, these Lozenge tilings can be interpreted as surfaces, random surfaces, whose boundary is pinned down by some boundary data, right? Which, as I mentioned before, doesn't actually depend on the tiling. It only depends on the domain. So I have some sort of random height function whose boundary data is pinned down. Okay. And the statement, the theorem, which goes back to Plum Canyon Prop in 2000, is that on large domains, on any large domain basis, I mean, you might have a few self-hypotheses, just smooth or simply smooth boundary or simply connected. I mean, something like this. Piecewise smooth boundary or simply connected. The height function, if I take a uniformly random Lozenge tiling of my domain at random, I associate it with its height function. The height function converges to some limit shape. It converges to some, it has some law of large numbers. Okay, so I should say a few, I won't write down the variational principle in thorough detail, but I just want to tell you a few properties of it, qualitative properties of it. The first is that it's strongly dependent on the geometry of the domain. And hopefully you can see that based on this picture over here, these 5 pictures over here, which I've drawn 5 different domains. The first is a hexagon. The second is some, I guess, octagon. Yeah, some octagon. The third is some sort of S-shaped polygon. The fourth is a triangle, but with jagged edges. And the fifth is a parallelogram. And as you can see, I've taken sort of a random Lozenge tiling of each one. And as you can see, they all look fairly different. I mean, on a global scale. Yeah, right. So, I mean, the limit shape that you'll see will inevitably depend very strongly on the domain. The one of these I can quickly explain is the parallelogram, which is maybe the most serious exemplification of this domain dependence. You can actually see fairly quickly that this parallelogram only has exactly one tiling. For instance, as you can see, if I tried to tile this domain, I start from the bottom corner. Only one tile will fit there, which is the one that's pointing up, right? Then the two next to the two above, I have some smaller domain. If I fill in that rhombus, I fill in the lozenge there, and then I'm again kind of forced to have 2 other vertical rhombi above it. And in this way, this kind of propagates up, and this only allows me to have one tiling of the full domain. And this is what we often call a frozen domain. So this domain is kind of boring, and the other ones are kind of more interesting. But hopefully that should already convince you that the limiting shape, or just in general the phenomenology behind these tilings, is strongly dependent on the geometry of the domain. The second point I want to mention is that it can be very inhomogeneous in the sense that sort of what you see, another way of saying it is like the density of tiles can differ very much depending on which part of the domain I'm probing. So you kind of don't see that for this trivial case, the rhombus, but already in the hexagon, I kind of alluded to it before. Namely, if I look somewhere in the middle, I'll see, equal proportions of all of the different types of tiles, pink, blue, and yellow. But if I look in the corners, I'll just see one type of tile, basically just one type of tile. The other 2 will be completely absent. So as I poke around different parts of the domain, I'll see different densities of these different tiles, and this is a sort of form of heavy spatial homogeneity. So yeah, these are 2 features about these Lozenge tilings, which makes their asymptotic behaviors fairly non-trivial. Okay, so a prediction that I want to mention that won't really be a focus of this talk at all. I just want to mention it. Since you have a lot of large numbers, it's a natural question to ask how the tiling fluctuates around it. And there's a prediction that goes back to 2005 by Kenyon and Alpunkov, which is that the fluctuations around this limit shape converge to the Gaussian free field. I won't talk too much about these fluctuation questions. I'll be interested in more in different questions for this talk, but I'll just mention for now that this is proven on various special domains, but in general is quite open. Okay, so what I'm actually going to be interested, what I'm actually going to be interested in this talk is microscopic features, but before I mention them, I just want to quickly say a few words about some macroscopic features. So depending on the boundary, as I said before, the limit shape can exhibit different behaviors, and we'll often refer to some of them as liquid or frozen. Okay, so frozen regions are sort of regions. I mean, these are just a qualitative definition for now, which is that a frozen region is a region where the tiling only exhibits. I mean, it's a little piece of the domain where I only see tiles of one of the 3 types. So for example, one example of a frozen region is shown over here in the bottom right corner, where as you can see, I only see these red tiles. Okay, so again, qualitatively, a liquid region is where I see all different types of tiles, and the associated surface will seem more rough and random. And you see that inside, sort of inside the circle. Now, there's typically going to be a curve separating the sort of liquid region from the frozen region, and we will often refer to this as an Arctic boundary. Okay, so as I said, I want to talk about local features rather than global features of this model. So zooming into different parts of this domain, I will see different limiting behaviors. And my goal is to understand the probabilistic features, the statistics associated with these behaviors. So let me take a few moments to describe what sorts of behaviors one kind of sees depending on where one probes. Okay, so one example is for me to probe like somewhere in the bulk of the liquid region. So I don't want to kind of probe in the frozen region. Otherwise, I want to see something trivial. I'm just going to see all lozenges of a single type. But let's suppose I probe somewhere in the liquid region. I'm going to see a bunch of tiles there. And so I see a bunch of tiles there. And the basic question is, what is the local law of these tiles I see? For example, what is the probability that I have two vertical tiles right next to each other at some point? Okay, sort of local correlation functions for tiles in the liquid region. So you're just kind of considering an order 1 by order 1 scaling there. Okay. Another example is near the edge of a facet, or alternatively near the Arctic boundary, where I see mainly tiles of one type. See over here, I kind of see mainly these green tiles, but I see a few of these defects, sort of these red and orange tiles, which will appear, and then one wants to understand the behavior of those. Yet another example is near the tangency location. Since the Arctic boundary will be tangent to might be tangent to the domain at certain points, and there we'll see a different type of behavior, which is that I see a few lozenges of one type. So here I'll see a few green lozenges, and I'll see a bunch of lozenges of the other types. And you'll be interested in understanding how the green lozenges are kind of distributed in this sea. Okay, so I'll try to explain. That was just an overall overarching description. I'll try to get into more detail about this later on. So the basic goal then is to understand the limiting statistics as I probe these different regions and see how they depend on the domain. Remember, I said that the global features depended very strongly on the domain, so it's natural to expect the local features too as well. And this is what we'll be interested in doing in this talk. So you can view this as comprising in 2 steps. The first is to sort of compute the limiting statistics as these sorts of statistical the quantitative statistics of these different phenomena for a special domain. And the second is to show that these statistics appear universally. As I vary the domain, these statistics will appear maybe in slightly different forms. Okay. So again, the goal is to understand these limiting statistics and how they depend on the domain. And we'll see that these limiting statistics often admit close connections to random matrix theory. So I'll kind of give you in broad strokes what the answers are, and then I will then go into each case sort of step by step and explain them in more detail and a little bit of the history behind them, and then what we can say about them. So okay, so the first, as I mentioned before, is if you kind of zoom into the bulk of the liquid region, and what you'll expect to see there is an ergodic translation invariant Gibbs measure of some slope. Okay, and so I'll explain again more of what that means. But eventually the theorem statement will be that this holds for very general families of domains. Okay, so the next example will be near the tangency location, and in the situation, you'll see a variant of what is known as the GUE, or Gaussian Unitary Ensemble Comers Process, and the sort of the maximal set of domains in which this could be proven will be sort of, again, there'll be a fairly general set of domains for which this can be proven. The third example, again, near the edge of the facet, we'll see what is known as the Airy process, or the Airy line ensemble, and the theorem sort of the maximal set of domains in which we can prove this will be a fairly wide set of polygonal domains. So I should say that there are many works prior to ours, which I'll give you a set of references later on, which establish these results on special domains. So let me kind of get more into specifics about each of these cases and what's known about them and what one can say about them. Okay, so let's first consider the bulk of the liquid region. So we'll consider some domain R, which is a subset of the triangular lattice. And we'll consider some uniformly random tiling of it. Okay. Next, we'll fix some vertex V in R, and we'll consider some order 1 neighborhood of it. So say some 10 by 10 box surrounding my vertex V. So I have this sort of green, as you can see, there's this sort of green box over here, and we'll zoom into it, and you see some sort of just a discrete set of tiles in that box. Okay, so I have some random tiling on my big domain R. So if I restrict to my like order 1 box, I'll get some random tiling on that order 1 box. And the question I'm interested in is, what is the law of this tiling? So another thing that people often like to do, which is sort of the same but just a different interpretation, is that I imagine the size of my domain R tending to infinity, and then I let my size of my box, my green box, also tend to infinity, but much more slowly. So like log n or something like that. If n is the diameter of the domain, then it's tending to infinity, but very slowly. In that case, what you'll see is a random tiling of an infinite plane, as this green box will kind of exhaust the full plane. But this full plane cannot actually see the boundary, right? This full plane, it's sort of exhausting this green box is exhausting the plane, but much more slowly than the domain itself is, and therefore the green box can't actually see the boundary. But we'll see that it can kind of feel it in a sense. Okay, so yeah, again, the bulk statistics question is basically what is the law of this random tiling? You can think of it as either the law of the random tiling on some 10 by 10 grid, some 10 by 10 box, or on some infinite domain that's sort of like 10 to infinity very slowly. Okay, so this in particular contains like all sorts of correlation functions of nearly neighboring tiles. And the general prediction is that it should, the limiting measure that I should see on sort of this infinite plane should converge to should satisfy translation 3 properties, which are known as translation invariance, ergodicity, and the Gibbs properties. Let me explain what those are. So again, the general prediction for the general prediction is that any candidate mu for some sort of bulk statistics or some sort of local statistics should satisfy 3 properties. The first is translation invariance, which means that the probability measure mu is invariant under shifts the lattice. The second is ergodicity, which means that if I can decompose mu as so say p mu1 plus 1 minus p mu2 for some p between 0 and 1, then the decomposition had better be trivial. So I better have mu is equal to mu1 is equal to mu2. So I can't sort of non-trivially decompose mu. And the third is some sort of sort of a Gibbs property, which tells me that if I sort of condition on every part of my lattice, other than some finite piece of it, then the conditional law of the tiling on that piece is just our uniform and random tiling. So these are 3 properties. And it's a theorem which goes back to the thesis of Sheffield that for any given proportion of tiles, ST and 1 minus S minus T, there is a unique ergodic translation invariant Gibbs measure, mu ST, of tilings of the full plane with that slope. So again, ST and 1 minus S minus T are proportions of the tiles. So S is sort of the proportion of vertical tiles, T is the proportion of horizontal tiles, and 1 minus S minus T is the proportion of these other horizontal tiles. And that's point to it. Okay, and we say that this Gibbs measure mu ST has slope as comma t because its height function h, the height function associated with it, kind of has, it can be viewed as a random surface, and that surface on expectation has slope st, as shown by this equation here. Yeah. Okay, so what I gave you so far was sort of an abstract characterization of what this candidate, right? The candidate for these local statistics should look like. Okay, there's actually a more explicit one, which I want to take a moment to describe in this slide. So any tiling M of some domain is determined by the set of all of its vertical tiling. So I'll set Xm to be the centers of all vertical Lozenge tiling, the set of all vertical lozenges in my domain. So for example, here I've drawn a Lozenge tiling of a hexagon, and I've drawn dots in the centers of all the vertical tiles. Okay, so this forms some subset of R2, right? And then the claim, which is sort of a very simple thing to check combinatorially, is that the full Lozenge tiling is just determined by the locations of the vertical one. So the locations of these dots determine all of the tiles in my tile. Okay, so then the question of what is the law of a tiling boils down to what is the law of this Xm, the set of all of my vertical tiles. Okay, so for this measure mu st, there's sort of an explicit characterization of what mu st is in terms of a determinant. Okay, so the statement is the following. So let's fix some st, which is kind of my slope my Gibbs measure, how can I ask myself, how can I tell whether, like, what is the probability of some set of points being centers of vertical tiles? Okay, and the answer is the following, which is that this probability under μst of some set of vertices x1, x1, y1, x2, y2, all the way to xm, ym, being vertical, centers of vertical tiles as a determinant. It's sort of a determinant of some n by n matrix, which I've called kc of xi, yi, xj, yj. Okay, so this k is an explicit integral, which is kind of looks like a beta integral, except it's cut off kind of. It's not going from the integral is not covering the full line, but only part of it, which is why it's sometimes known as an incomplete. This is sometimes called the incomplete beta kernel. And this C here is some explicit function of S and T. So in particular, each entry of this matrix is explicit. And therefore, if I wanted to ask myself, what's the probability that 0, 0, and 1, 1 are centers of vertical tiles, I could just compute a two-by-two determinant and get the answer. Okay. So in particular, this is fairly useful for computing local correlation functions. And one example, which I can just show you a formula, is that if I ask myself for the probability that there are two neighboring vertical tiles, the probability of that happening under this μst measure is s squared minus sine squared pi s over pi squared. Okay, so this is some explicit formula. And for those of you who like random matrix theory, you might recognize this as sort of a discrete analog of the sine kernel that arises in random matrix theory. Okay, so this is all, okay, so what I've done so far is I've told you a candidate for the Gibbs measure, which everyone believes to really be, a candidate for these local statistics, which everyone actually believes to be the local statistics. But okay, but now it's a question of how do you actually prove that the local statistics are given by this measure μst? Okay, so here's a theorem which states the following. Okay, so let's fix some domain R. Okay, so simply, so I'm going to start on the continuum, and then I'm going to sort of discretize everything. So we'll start with some simply connected subset R of R2. So I can imagine it being something like this for the moment. Okay, with piecewise smooth boundary, and we'll take some big integer n, which you should kind of view as like the diameter of your domain, and we'll consider some tailable domain R or Rn with the property that if I scale down this this Roman R by n, I get the math frac the frac R, which is this continuum domain. Okay, so next what I'll do is I'll fix some vertex v in my continuum domain, and then I'll scale it up to get some vertex, which I've called this Roman v in my discrete domain, and we'll let n, or depends on n again, be some uniformly random tiling of my discrete domain. Okay, and the question is, what do the local statistics look like around this vertex v? And the theorem is that under this level of generality, so for any sort of, if I just started with some simply connected subset with piecewise smooth boundary, then the statement is that the local statistics on and around v are given by this measure μst from before, where st is the gradient of the limit shape of the tiling around v. So remember these height functions can be interpreted as random surfaces or as surfaces which have a limit shape. I can take the gradient of the limit shape of the sort of limiting surface, and that's going to be my st. Okay, and then the theorem is that indeed the local statistics converge to this μst. Okay, so this is predicted by Kunkany and Prop in 2000, and you can see that these local statistics they contain a ton of information, right? They contain sort of all local correlation functions of tiles. I can ask myself, what's the probability of having a tile at a vertical tile, let's say 0, 0, 1, 3, 5, 7, 10, 5. I mean, they can sort of infinitely many correlation functions, but at the end of the day, the dependence of these bulk statistics is just isolated on the dependence of how these local statistics depend on or these correlation functions depend on the domain. It's just isolated in two parameters. So you have this kind of huge level of dimension reduction essentially happening, which one often refers to as universality. So that's why the title of the talk is universality. The dependence on the domain. I mean, the domain is the set of domains is sort of infinite dimensional, but at the end, all these local statistics will depend on the domain through just one or two parameters, basically. Okay, so that concerns the bulk of the liquid region. let me now pass to near tangency locations. So let's fix a point where the Arctic boundary, again, the boundary between liquid and frozen regions, is tangent to some edge of my domain. So let's say it's tangent to a horizontal side of my domain. Okay, so as from in the bulk case, we looked at like sort of order 1 by order 1 neighborhoods. In this case, the proper scaling will be square root of n by 1 neighborhood. So where n is the diameter of the domain. So we'll fix this point, this sort of this blue region where my Arctic boundary is tangent to the sort of south boundary of the domain. And we'll consider some like n to the 1/2 by 1-ish, like 10 times n to the 1/2 times 10 neighborhood of that region. Okay, and what you see is the following. You'll see sort of that most tiles are of 2 types. And these 2 types are sort of the types of the frozen regions on either side of the tangency location. So over here, I see orange tiles, and over here, I see red tiles. So if I zoom in, I'm mostly going to see orange and red tiles, but there are a few defects, and these defects are given by these green tiles that appear every once in a while. So you can see that these green tiles, just by this example, and it's not so hard to convince yourself combinatorially that this is true, but these green tiles form an interlacing array in this neighborhood. So like every green tile on this green tile is between the 2 green tiles above it, which is between the 2 green tiles above it, and this is between the 2 green tiles above it, etc. So like sort of there are no any 2 consecutive green tiles in row K has some green tile below it in row K minus 1 that lies in between them. Okay, so let's denote the locations of, so I mean, again, so the locations of these green tiles basically recover the full picture, as I said before. I mean, the locations of the vertical tiles always enable to recover the full tiling. So let's denote the locations of the positions of these vertical tiles on level K by x1k, x2k, all the way up to xkk. It turns out that there are k such tiles on level K. Okay. So for example, here is x11, here's x12, x22, here's x13, x23, x33, etc. Again, the tangency statistics question is, what is the joint law of all of these xik's? Okay, so this is where the GUE Comers Process comes in. So let me state what sort of the limiting answer is, and then I'll state on this sort of on one specific domain, which was originally computed, and then I'll state sort of the result on the most general family of domains for which we know it. Okay, so the first family of domains for which this was probed was the hexagon. This is just one citation of many. I'll have references. I'll give you a more complete list of references later on in this talk. Okay, so Nordenstrom considered the hexagon of side-length n, and he showed that there exists constants mu and sigma. I mean, they're explicit, for which the following holds. So if I take my xk's, I subtract off mu n, so I kind of subtract off some linear term, which you think of as a law of large numbers, and then I divide out by n to the 1/2. So I have like sort of a diffusive central limit type scaling. This will convert to some set of numbers, CIK. And this CIK is a set of random numbers that can be described explicitly as a sort of they're known as a Comers process. So so this CIK can be defined as well. So we'll let X which denotes some infinite array of independent standard complex Gaussian random variables. So each entry, the ij entry of this domain is xij. I'll let M denote a half times x plus x transpose. So this is or x plus x conjugate, right? So this is going to be some infinite Hermitian random matrix, and then I'll cut out corners of this matrix, as shown over here, and we'll let M superscript k denote the k by k matrix obtained by cutting out the top left k by k corner. Okay. Then we'll let C1k, C2k, all the way to CKK denote the eigenvalues of this mk. And so this is the standard fact from linear algebra that these CIKs interlace, just as the XIKs do. So it shouldn't be, so it shouldn't be completely crazy to expect that you have this sort of convergence happening over here. Okay. So this is again, so Nordenstrom analyzed it on the hexagon, and there have been a number of results which I'll mention later on that have done this in more general domains. But for now, let me mention a theorem which tells you sort of the most general family of domains for which we know this result. So let's again fix some R, some subset R. of R2, which has 3 adjacent segments that are inclined at 120-degree angles with respect to each other. So for example, over here, I mean, as a depiction, I've shown this R over here, which has 3 adjacent segments which are inclined at 120-degree angles with respect to each other, and then can do whatever it wants outside of that. I can go completely crazy outside of that. I don't care. All I care about is that it has sort of 3 inclined segments I've shown over here. Okay. Okay, so then we'll let R, we'll call it Rn, be some sort of n-fold blow up of the domain. So I just scale it up by n. We'll assume it to be tellable. Okay. We'll next let Mn be some uniformly random tiling of this domain Rn. And okay, so what will happen is that again, you'll have near this horizontal segment down here, you'll have a family of vertical tiles. Okay. So we'll denote the x coordinate as we did before, we'll denote the x coordinates of the vertical tiles around this horizontal segment by xik. And so the theorem is that for this general family of domains, there exists constants mu and sigma, so that basically the same result as before for the hexagon holds for these holds in general. So this if I subtract off mu n from these xiks and I scale down by n to the 1/2, then they converge to some ciks which are given by the GUE Comers process. So this is predicted by Johansson and Nordstrom in 2006, and I should say that it's false if I drop this. So here, I mean, the domain was almost general, except I imposed that I have these sort of 3 horizontal segments. I mean, I have these 3 segments inclined at 120-degree angles with respect to each other. And I should say that this can fail. I mean, the theorem can fail if you drop that assumption. So for example, if your segments, if one of your 3 if your segments here, if they even have one microscopic dent, so I mean, so even if they macroscopically look like 120-degree angles, but they just have a little tiny dent, as shown over here, the Comers process will break, so it will be false. So there's almost a sense in which this is, I mean, it's depending on your interpretation, this is almost an optimal condition. So yeah. Okay, so next I'll pass to the third regime, which is near the facet edge, sort of the edge between the bulk and sort of the liquid and the frozen regions. And I remind you that the terminology was that we called the boundary between the liquid and frozen regions the Arctic boundary. Okay, so let's fix some sort of smooth point on the Arctic boundary that is not a tangency location. I just told you what happens on the tangency locations. So you have to not be at a tangency location for this to be correct. Okay, so we'll take some n to the 1/3 by n to the 2/3 neighborhood of this point. So this is yet again a different scaling. And this rectangle will be of a fairly specific, I mean, it will have a specific orientation. In particular, the n to the 2/3 direction will be sort of parallel or tangent to the Arctic boundary. And the n to the 1/3 direction, the n to the 1/3 side will be orthogonal to the Arctic boundary. Okay, so actually this sort of rectangle here should be kind of slightly slanted a little bit. Okay, so since I'm near the facet, or the facet only has, the frozen region only has tiles of a single type. So you should imagine that if I'm right next to it, I'll have mainly tiles of that one certain type, but plus a few defects. Okay, so in this case over here, I have mostly tiles of this green type, but then a few of these red and orange tiles. Okay, so if I only consider the defects, so I erase all of the green tiles, then I get a picture that say looks like this. And what you see when you look at this picture is sort of a family of non-intersecting paths. So these sort of the red tiles are kind of taking steps of this path to the right, and the orange tile takes a step of the tile to the left, of the walk to the left, of the path to the left. Okay. So yeah, these red and orange tiles, they form a family of discrete left-right walks or paths, and we'll denote them by x1, x2, etc. Where x1 is sort of the extreme one, x2 is the next most like sort of next one, etc. And this xi will index by xi of t. So xi of t denotes the location of the ith path at vertical slice t. Okay, so you can kind of view t as time and x as position. Okay, so this extreme path, the leftmost in this picture, the leftmost path, is exactly the interface between the facet and the liquid region. It's exactly where I stop seeing only green tiles and start seeing a little bit of the other tiles. Okay. Okay, so then the edge statistics question asks what is the joint scaling limit of these? I mean, I can recover the full tiling if I know where these walks are. So the edge statistics question asks, what is the joint law of all these paths, of all these x1, x2, x3, etc. Okay, so again, I'll give you the result. I'll start by just giving you the result on a specific domain. I'll tell you sort of what the most general family of domains for which you know the result is, and then I'll talk about other results previously. Okay, so on the hexagon again, sort of which is among the simplest domains, the theorem, which goes back about a decade or so, is the following. If I take my xi, I look at time, so I look in the vertical direction, again, sort of parallel to the Arctic boundary, of order n to the 2/3, so like there's some scaling, there's some, these a, b, and c are just scaling, they're just constants. One can compute them if one likes, but I won't write down the formulas for you. So if I sort of look at xi of t times n to the 2/3, this will first, and then I subtract away some law of large numbers for it, and I divide down by n to the 1/3. This will converge to what's known as to this family of curves, this curve ai of t plus some shift t squared. Oh, sorry, plus some shift t squared. So this is some limiting random continuous curve, and this family of curves AIT, which is like A1T, A2T, etc. So these are like, you imagine that these are like the scaling limits of the left of these extreme paths near the boundary of the liquid region. This family of curves is often known as the Airy line ensemble. So it's a family of continuous, random, non-intersecting curves, A1, A2, A1, A2, etc. And I think this name was given by Carwin and Hammond back in 2011, who also showed it sort of defined it in a pathwise sense. This is a fairly prevalent object in the Carter-Parisi-Zhang or KPZ universality class. For example, its top curve is what's known as the Airy process, which is ubiquitous in the KPZ theory. So I don't want to give you a full definition of this Airy line ensemble, but I'll just quickly mention that it's a determinate point process like we had before, but with a different kernel. So the kernel now is going to be written in terms of Airy functions instead of in terms of some incomplete beta kernel. And it's sometimes known as the extended Airy kernel. So this Airy line ensemble appears again. It's related to random matrix theory, like the previous two limiting phenomena were. It's the edge, sort of the edge limit of Dyson running motion, which so a picture shown over here, where I have these paths, and at the edge they converge to something, and these paths at the edge, we've zoomed into the edge over here, and this is sort of a picture of the Airy line ensemble. Okay, so now I should tell you what the result is on sort of the most general families of domain for which we can prove it. So we'll fix some polygon P with sides parallel to the axes of T, which satisfy certain technical conditions. I'll mention these technical conditions in a second, but they're sort of non-generic. So you should imagine P being something like sort of generic choices for its side lengths. Okay, and then this sort of statement should hold. But I'll tell you what I mean in a second when I say these technical conditions. Okay, then we'll fix some smooth point V on the Arctic boundary, and we'll define P to just be I'll blow up. I'll define this Roman P by blowing up this continuum polygon by a factor of n. And we'll let V denote just, again, I'll multiply this continuum V by a factor of n, and it's some vertex in my domain. As usual, we'll let this M or Mn be a uniformly random tiling of P, and then we'll consider the family of discrete random walks near this point V, which is on the Arctic boundary. Okay, the theorem sort of stated somewhat informally, but hopefully you can imagine what it means, is that under the previous sort of renormalization, this n to the 1/3 normalizations of this n to the 1/3, n to the 2/3 scaling, as shown over here, I'll again have the same convergence to the Airy line ensemble. It's just that these constants will be different. Okay. So I owe you what I mean by these technical conditions. So these are conditions on the Arctic boundary. So this Arctic boundary, it can have it's an algebraic curve. It can have certain singularities. Generically, the singularities are just cusps. But occasionally, if you tune your boundary, if you tune your sort of domain just right, you can have other kinds of singularities. So some examples of these singularities are what people call technodes or cuspidal turning points. Or so basically what I'm asking is you have none of these sort of weird singularities, and you also have no two cusps are on exactly the same horizontal level. So I can have two cusps that are, sort of, I can't have two cusps that share the same y coordinate. And again, you kind of generically expect that to be true. Okay. So I should say that our results are by no means the first results in this direction. There's a massive literature on this topic, and the slide, which attempts to list at least some of them, is probably not complete by any metric, but I'll still try to explain some of these results and methods, and then I'll try to explain our what we used. And Mark, maybe you can remind me, do I have 50 minutes or an hour?
50 minutes and then questions.
Okay, sounds good. Okay, so I will just quickly mention these results. I'll say just a few words on the proofs, and then I'll conclude. Okay, so it's a result that goes back to Castellan back in 1961, that random tilings are determinant of point processes, in the sense that correlation functions for these random processes can be written in terms of a determinant of some matrix. Now, this matrix turns out to be very difficult to analyze in general, and there are a number of tools that people have developed for trying to analyze these matrices. So first is just to directly compute the entries of this inverse Castellan matrix and show that they converge to some scaling limit. So these results here kind of did that on the torus and on certain families of hexagons. Another approach is to sort of get out the kernel, or get out the Castellan matrix through the approach of orthogonal polynomials, which was fairly fruitful in the context of a slightly different tiling, domino tiling from the Aztec diamond, also on hexagons. Another approach is via representation theory. So there are actually a lot of different representation theoretic tools here. The Schur processes, Schur generating functions, Gauss-Settlement paradigm. There's a fairly wide list of techniques here. This was fairly fruitful in the context of skew plane partitions, or of sort of trapezoidal domains. And there are other sorts of probabilistic tools that kind of apply by piecing some of these together in some probabilistic way that I won't go into too much detail about. And as you can see, like one way, the kinds of domains that were addressed in this way kind of address domains that were combinations of these domains in some way, like domains covered by trapezoids, which were in turn covered by representation theory. And also, if I kind of perturb my domain by a little bit, by some constant number, then you have some stability and things like this. So now I should say that sort of a general issue in most of these approaches, I mean, not all of them, but most of these approaches, is that they're based on some determinantal method, and computing the entries of this determinants on arbitrary domains turns out to be generally quite challenging. It's really only known how to analyze this determinant on very special families of solvable domains of the type that I kind of listed over here. Okay, so I just want to say one quick slide on the proof, sort of in vague overarching terms, and then I'll conclude. So to show these universality results, what we'll instead do is we'll sort of locally couple, again, these are local statistics. So in general, two domains, they exhibit wildly different behaviors, but locally, again, these theorems are really telling you that they should exhibit sort of similar behavior. So what we'll do is we'll locally couple the tiling on a general domain to one on a solvable domain. And this requires sort of three steps. The first is an analytic step, which is to sort of show some sort of a priori bound of the tiling on your general domain. So here you really have to face the general domain, in the eye, and show some a priori, some coarse bound that doesn't necessarily address the limiting statistics, but maybe show some concentration results for a general domain. Okay, the second is sort of an algebraic step. You have to locate sort of a solvable domain for which you can get your hands on, for which you can actually show these fine-scaled universality, like these sort of fine-scale local statistics, like these incomplete beta like this bulk statistics, or these GUE Comers Process, or these Airy line ensemble. You find one domain for which you can actually prove that result. And the third is a probabilistic step, which is you use the analytic step to prove the existence of a coupling between your original general domain and your solvable one. Okay, so for example, you might try to say in some local neighborhood, you might try to sandwich your tiling on your original domain between two tilings between two solvable domains. Like you kind of try to squeeze your tiling on locally, squeeze your tiling on your general domain between two solvable tilings. Okay, so I should say that the implementation for this sort of general framework in these different regimes is very different. So at the tangency locations, the estimate is just a sort of a subdiffusive bound. So you want to like a little O event to the 1/2 concentration estimate. And the family of solvable domains is the family of trapezoids. At the edge of the facet, you actually need a much stronger concentration result, which is why sort of we showed it for only polygons and not for fully general domains. You need an order n to the delta kind of concentration estimate for the height function. The family of solvable domains was actually just hexagon, so the simplest family of solvable domains. And in the bulk of the liquid region, what you needed was a local, we often call it local law of large numbers, which was sort of initiated, like sort of popularized in the work of Erdős and Yau in the context of random matrix theory. And the family of solvable domains is sort of an infinite trapezoid. So I don't have much time left. I think I'm basically out of time. So with that, I'll just summarize. So I should say that random Lozenge tilings are very sensitive to their boundary conditions. That local behaviors differ wildly depending on which domain one takes and where one probes in the domain. So in the bulk of the, however, sort of local behavior should exhibit sort of universality phenomenon. And in the bulk of the liquid region, you should see this sort of ergodic translation of Invariant Gibbs measure. At the tangency locations, you should see these GUE Comers processes. At the edge of the facet, you should see the Airy process or Airy line ensemble. And we have recent results that establish these phenomena are sort of universal and that they appear for fairly general classes on fairly general families of domains. And the proofs are based on a combination of algebraic, analytic, and probabilistic methods. The analytic method is to just obtain some coarse estimate on your general domain. The algebraic part is to obtain refined asymptotics for a specific domain. And the probabilistic is kind of the glue between the two that allows you to couple your general domain to the algebraic one, which allows you to conclude. So with that, I'll thank you for your attention.
All right. Thank you, Amol. Does anybody have any questions? So one question I have that might be a little bit silly. So if you're looking at sort of the edge, you see the Airy line ensemble.
Yeah.
There's like limits you can take of the Airy line ensemble that should give you something about the KPZ fixed point. Should you be able to see the KPZ fixed point in these models if you take like the right kind of limit near the edge, or should that not?
You don't see the general KPZ fixed point. Now there's a sense in which the KPZ fixed point is kind of embedded in the Airy line ensemble, but this is not. I mean, it's a somewhat complicated functional of the Airy line ensemble. So this is not sort of a natural functional from the terms of tilings. So from that perspective, you don't really see the Airy line, like the KPZ fixed point in these tiling models. And one sort of concrete manifestation of the absence of the KPZ fixed point is that the KPZ fixed point, sort of locally, it's some sort of stationary. Like locally, it has some sort of you can imagine it being sort of stationary locally, and locally, sort of the stationary local statistics for the KPZ fixed point are given by kind of bike range type distributions. But you never see a bike range distribution in these tiling models. So yeah.
Okay.
I had a question about the results for the bulk rates. Yeah. Two things. Given a general region, I guess it's the fractal R. Can one say anything about the values of S and T? Are there approximations or are there bounds?
So what you have to do is you have to compute the limit shape. So what you would do is you solve some variational principle on this math frac R domain. Okay, so there's some variation principle, sort of an explicit Lagrangian. One could write it down if one wants. You solve some maximization problem on this domain, so it's some which basically reduces to some elliptic PDE. And then so this gives you some function on R. You look at the function at this point V, and you take the gradient of that function at V, and that gives you your ST. So you have to take some gradient of some solution to a variational principle. Now, you want in general, for completely general R's, you actually can't really get an explicit formula for the solution to this variational principle, but you can say qualitative things about it. For example, we'll have like elliptic regularity. So I mean you'll have big analytic estimates, but if you want to say some explicit formula for it, I mean this is not something one can easily do.
Yes. So for example, you showed us early on the lozenge, which had only tiles of one sort, which is like an extreme case. Can one identify all the extreme cases where one of the S and T is 0 or 1 and
Oh, they can be anything. ST could be anything here. In the bulk, so in the bulk, this ST.
But if I'm given a region R, then S and T are characterized somehow by R.
Yes. So the statement is I fix some domain R.
Yeah.
I fix some point V in R, and then whatever that ST and T happen to be, that's your answer for the bulk statistics. So in particular, that doesn't impose any restriction on S and T. They could be anything.
They're not determined by the region R.
They are determined by the region R, but I mean they're
Okay,
not.
so the question is, can one say anything about how they are, even if you cannot do it explicitly, because it's a particularly nice region R? Are there still estimates? Are there bounds? Are there approximations?
Oh, you want to know if one can compute S and T explicitly?
Or even just bounds away from the extreme cases where
So,
S and T are 0 or 1?
Yes, so you can, right? So it will depend on where your vertex V is. So if your vertex V is kind of close, if your vertex V is of distance some d from the Arctic boundary, so you have this right? So you have this Arctic boundary. Of course, if your V is here, then you're in trouble, where your S and T are definitely going to be 1. If you're here, if you're inside the Arctic boundary, then your S and T are going to be bounded away from 1. And as you approach the Arctic boundary, as you get, say, within maybe some distance d, d of the Arctic boundary, your distance from some trivial choice of ST will decay like a power in d. It'll be like d to the maybe 1/2, I think. So that's, I guess, that's some sort of qualitative statement about how bounded away your S and T are depending on where your V is from the trivial regions. Yeah.
So the trivial region would be where the Arctic boundary.
Yeah.
I guess there's no Arctic boundary and everything is the Arctic.
Sorry?
I said, so the trivial case then would be where everything is the Arctic.
Arctic and outside of Arctic, yeah.
Okay.
And then if you're in the liquid, if you're sort of inside the circle, then you're non-trivial. And I was trying to just describe to you how non-trivial degenerates to trivial as you get closer and closer to the Arctic boundary.
Okay, thank you.
Yeah.
Okay, other questions? So I know there's supposed to be some there's supposed to be for some like periodic models, other regions that are like a gaseous region. This is something that doesn't occur at all in uniform tilings.
Yeah, so in Lozenge Tilings, these don't appear. There are models for which this appears. I haven't really thought about them though, so I don't know to what extent the results can be extended to them.
Okay.
I think someone is trying.
Okay. Do people have other questions? All right. Let's thank Amol for this great talk.
Thank you.
Thanks again.